everybody, it's Miss Manili again. And in today's lesson, I'm going to introduce to you the concept of a unit circle. And in doing so, we're going to talk about a unit circle, which is basically a circle that has a radius of 1. We're going to look at all of the common angles that we use in trigonometry and in geometry. For example, a 30, 60, 90 degrees, 45-degree angles. Those are all really common angles that we use with trigonometry. And we're going to be looking at the radian measures as well as the degree measures, but we're also going to be looking at our three most important trig functions, sine, cosine, and tangent, and we're going to be able to, in fact, evaluate those functions for different angles without the use of the calculator. So we're going to start by doing a quick review of some basic geometry in terms of right triangles. If you remember a right triangle, if you wanted to find the length of the sides, the longest side of a triangle is called the hypotenuse. And if I wanted to look at the relationship between the three sides of a triangle, as long as it's a right triangle, I know from the Pythagorean theorem that the sum of the squares of the two shorter sides are going to be equivalent to the square of the hypotenuse. So we know that a squared plus b squared equals c squared. So if we take a look at number 2, we're given two right triangles and each has a missing side. So in letter A, we've got a triangle that has a length that's 3, a length that's 4, and then our hypotenuse is unknown. So if I want to calculate this, I know that I'm going to take 3 squared plus 4 squared, and that's got to be equivalent to c squared. Well, 3 squared is 9, 4 squared is 16, and so that's going to be 25. So c squared is equal to 25, and if I take the square root of both sides, I know that c then is 5. And that's actually a really common relationship, the 3, 4, 5 triangle. If we take a look at letter B, notice now it's the shorter side that's missing. So if I think about my equation, it's going to be a squared plus 12 squared is going to equal, 15 squared. Well, 12 squared is 144, and 15 squared is 225. And if I subtract 144 from both sides, I get that a squared is equal to 81. And if I take the square root of both sides, I get that a is equal to 9. Okay, in number 3, you're actually given two of the most common types of triangles that we're going to see, a 45, 45, 90, and a 30, 60, 90 degree. Now, I learned from my last class that this is not something that they remembered from geometry, but if the length of our hypotenuse is 1, there are certain relationships among the other two sides. The 45, 45, 90 is pretty straightforward. If I call this side A, then I know this length is also A. And so I know that a squared plus a squared has to equal 1 squared. Well, a squared plus a squared is going to be 2a squared, and 1 squared is just 1. So if I solve for a, I'm going to divide both sides by 2, and I get that a squared is equal to 1/2. If I take the square root of both sides, then I get that a is equal to, well, the square root of 1 is just 1, and that leaves me with the square root of 2 on the bottom. Now, again, for this course, it was expected that you guys understand how to rationalize a denominator, but what I learned from my last class is that is not something that they remembered from geometry. So we have a lot of rules when it comes to fractions. Fractions always have to be in lowest terms. If you remember when we were dealing with imaginary numbers, we're not allowed to have an I in the denominator of a fraction. Well, the same is true with the square root symbol. That's called a radical sign. We're not allowed to have any radicals in the denominator of a fraction. So similar to what we did with imaginary numbers, if I want to get rid of the square root of 2, I'm actually going to multiply the whole fraction by 1. But instead of multiplying by the number 1, I'm going to multiply by the square root of 2 over the square root of 2. I know that that's going to reduce to 1, so I'm not changing the value of my fraction. But when I do this, 1 times the square root of 2 is going to stay the square root of 2. And when I multiply the square root of 2 times the square root of 2, I get the square root of 4. And the square root of 4 is simply 2. And so this is the correct way to express 1 divided by the square root of 2. I rewrite it as the square root of 2 over 2. And so that means if I have a 45, 45 degree or 90 degree triangle, that the length of my sides is going to be the square root of 2 over 2, the square root of 2 over 2. And that's if I have a hypotenuse of 1. The relationship for a 30, 60, 90 degree triangle is a little bit more complicated, and since it's not part of this course, it's something that is now covered in geometry. I'm not going to go through the calculations. I'm just going to tell you that the length of the shorter side is going to be 1/2, and the length of the longer side is going to be the square root of 3 over 2. And that relationship's always going to be the same. So for example, if I'm dealing with a 30, 60, 90 degree triangle, and I tell you the length of the side is 5, then the length of the shorter side is just going to be 5 times 1/2, or 5/2. And the length of the longer side is going to be 5 times the square root of 3 over 2. We're going to be using these relationships in class today. That's why I wanted to review them pretty quickly. Okay. So in a minute, I'll relate what we just did with the triangles to what we're going to be doing with circles. Right now, I know it's a little confusing. We're going to start, and in class we actually did a paper plate activity to kind of understand this, which I can't really do using my smartboard. But if we take a look at what is called a unit circle, and I know that that doesn't make a lot of sense right now, but basically if I take a circle and I plot it so that the center of my circle is at the origin and I have an X, oops, that doesn't look like, let me actually make that neat. If I have, you know, my x-axis here and my y-axis here, sorry, it looks like that's a little bit off. I didn't mean to make that disappear. There we go. And I'll make this go up a little bit. Okay, so if I take a circle and I plot it on the x and y axis, so this is my x-axis, this is my y-axis, what I'm going to do is look at all of the angles that are the most common angles that we come across in geometry and in trigonometry. And what I'm going to do on the dotted lines is I am going to write all of the degree measures. So if I'm talking about all my angles in standard position, which means that I'm always starting on the x-axis, that makes this a 0-degree angle. I'm going to start with my most common angles. Obviously, my y-axis is going to correspond to a 90-degree angle. If I continue all the way around, this is going to be a 180-degree angle. And so now, if I'm looking at the quarters, I know they're each 90 degrees, so if I add another 90 degrees, I'm going to be at 270 degrees. And if I add another 90 degrees, it turns out that a 0-degree angle is equivalent to a 360-degree angle. The next thing I'm going to do is take a look at the angles that are bisecting my quadrants. So for example, this angle right here. Okay, since it's bisecting that quadrant, it's going to be a 45-degree angle. And now if I count by 45 degrees, so here's 0, I'm going to start here, this is 45. If I add 45, that puts me at 90. If I add another 45, that's going to put me at 135. If I add another 45, I know that's going to put me at 180. Another 45 is going to be at 225. I'm going to make sure that's in the middle. If I add another 45, that's going to give me 270. And another 45 is going to give me 315. And if I add another 45, I'll be back to 360. So now I've done all my 45-degree angles. The next thing I want to do is take a look at my 30 and 60-degree angles. And if I just count by 30s, basically I'll have the rest. So now I'm looking at these angles here. Okay, since I'm basically taking my quadrant and dividing it into thirds, if I take a third of 90, I know this is going to be a 30-degree angle. If I add 30, this is going to be a 60-degree angle. If I add 30, I'll be at 90. If I add another 30, that's going to give me 120. Another 30 is going to give me 150. Another 30 puts me back at 180. Another 30 puts me here, and that's going to give me a 210-degree angle. Another 30, 240. Another 30 puts me at 270. Another 30 puts me at 300. And another 30 puts me at 330. Whoops, let me make sure I put that on the dotted line. And if I add another 30, that gives me back to 360. So now I've essentially labeled all of my angles in terms of the degrees. And these are the most common angles that we're going to come across in trigonometry and in geometry. And if you look at the pattern, notice that from the first point to the second point is a difference of 30. Then it goes 15, 15, 30. 30, 15, 15, 30. 30, 15, 15, 30. 30, 15, 15, 30. And so if I asked you to reconstruct the unit circle, which I will have you do, you're actually going to need to commit this to memory. And I know it's probably freaking you out that I just said that, but it's actually really easy. There's only a few numbers that you really need to remember. Otherwise, it's just patterns. And if you can remember the patterns, it's really simple to reconstruct. So after we label all of our degree angles, we want to go back and label all of our radian measures. So I'm going to do that in red. And again, I'm going to start with my 4 quadrants. I know that a 0 degree angle is going to correspond to 0 pi. I also know that a 180 degree angle is going to correspond to pi. And if I go back around, to 0 pi is also going to be 2 pi. So if I look at my 90 degree angle, it's got to be between 0 and pi, so that makes it 1/2, or simply pi over 2. So each of my 90 degree angles, I'm adding pi over 2. So I start with 0 pi, pi over 2. This is going to be 2 pi over 2, which is equivalent to pi. Then if I add another pi over 2, this is going to be 3 pi over 2. And if I add another pi over 2, I get to 4 pi over 2, and 4 pi over 2 just reduces to 2 pi. If I deal with my 45 degree angles, okay, if you remember from the last lesson, if we take a 45 degree angle and multiply it by pi over 180, this is just equivalent to pi over 4. And so I know a 45 degree angle is going to be pi over 4. And so all those blue dots, if you can still see them, all of those blue dots correspond to a 45 degree angle. So instead of adding 45 and adding 45 and adding 45, I'm going to be adding pi over 4. So this is 1 pi over 4. My 90 degree angle is going to be 2 pi over 4. Well, 2 pi over 4 is going to reduce to pi over 2. And if I add another 45 degrees, this is going to be, so we had 1 pi over 4, 2 pi over 4. This is going to be 3 pi over 4. And then 180 degrees is going to be 4 pi over 4. And then we've got 5 pi over 4. 6 pi over 4 is going to reduce to 3 pi over 2, 7 pi over 4, and then finally 8 pi over 4 gives us back to 2 pi. If I deal with a 30 degree angle, 30 degrees, if I multiply by pi over 180, is going to correspond to pi over 6. So I know every 30 degree angle, all of those green dots that you see, are going to correspond to one measure of pi over 6. So this is going to be pi over 6. This is going to be 2 pi over 6. But 2 pi over 6 reduces to pi over 3. This is going to be 3 pi over 6. This is going to be 4 pi over 6. But 4 pi over 6 is going to reduce to 2 pi over 3. And then I'm going to have 5 pi over 6. 6 pi over 6 is going to reduce to pi. This is going to be 7 pi over 6, 8 pi over 6, but 8 pi over 6 is going to reduce to 4 pi over 3. 9 pi over 6 is going to reduce to 3 pi over 2. 10 pi over 6 is going to reduce to 5 pi over 3. And then the last one is going to be 11 pi over 6. And so let's take a look at all of our radian measures. Notice the denominators of all your fractions. We've got pi over 6, pi over 4, pi over 3, pi over 2. And then we go in the opposite order. This is going to be over 3, over 4, over 6, and then we don't have a denominator. And then it's over 6, over 4, over 3, over 2, over 3, over 4, over 6, and then no denominator. So if we look at the numerators now, I know that everything in the first quadrant is 1 pi on top. If we take a look at the second quadrant, take a look at the relationship between the numerators and the denominators. All of our numerators are 1 less than our denominator. So we've got 2 pi over 3, 3 pi over 4, 5 pi over 6. So all of our numerators are 1 less. If you take a look at the third quadrant, all of our numerators are 1 more than our denominator. The last quadrant's a little bit harder to see, but if you double the denominator and subtract 1, it gives you the numerator. We'll practice some of these patterns again, but it is important that you start recognizing the patterns so that you can recreate this unit circle whenever you need to. The last part of our unit, or of our lesson, is going to be to now identify the coordinates of each of these points. Okay, I need to find the x and the y values. So we're going to start, I'm going to go back to the beginning of my lesson, which I kind of skipped, and we're going to talk about what a unit circle is. There's 6 basic trig functions that we will use over and over throughout the course. So we know sine, cosine, tangent, but there's also secant, cosecant, and cotangent that are also functions that we can use. We're just going to discuss the first three today because those are the most common. There's two ways that we can define these functions, each having its advantages and disadvantages. The first way we're going to look at them is as points on a unit circle. We'll also relate them to triangles at the end of the lesson. So a unit circle is basically a circle that has a radius of 1 unit. That's a unit circle. The center of the circle is going to lie on the origin of our coordinate plane. If we construct a ray from the center of our circle, and actually let me rewrite that so that line isn't there. So here's my initial side. If I construct a ray and I identify the point at which it crosses my unit circle, I can identify that as the point xy, since I've superimposed my unit circle onto a coordinate plane. Well, if I drop an altitude, if you remember from geometry, dropping an altitude is basically dropping a line that's going to be perpendicular to the base. Well, by definition, I know the hypotenuse of this triangle, because it corresponds to the radius of the circle, is going to have a value of 1. Because the coordinates of this point right here are going to correspond to my x and y values, I know that this point is x, and if I go across to the y-axis, this is my y value. So if I'm looking now just at the triangle that I've created inside my circle, I can also identify the length and the height, or the altitude and the height, or the base and the height of my triangle. So this side right here is actually going to correspond to the y value. And this side right here is actually going to correspond to the x value of this point on my unit circle. And that's going to be really helpful. So let's go ahead and start identifying some of the points from those common angles that we created. The 4 easiest ones to label are going to be our x and y intercepts. So for example, remember our radius is 1. And so if I want to find the coordinates for this point, I know it's just going to be 1, 0. The coordinates for this point, the x value is 0 this time, but the y value is 1. For this point, it's going to be negative 1, 0. And for this point, it's going to be 0, negative 1. And so now we can take that information and go back to the circle and put those points in. So this is the point 1, 0. This is the point 0, 1. This is negative 1, 0. And this is 0, negative 1. So I've got a bunch of other points that I still have to find. Let's go back. Okay, let's start with our 30-degree angle, because that's the first one. Well, first of all, we said that 30 degrees, if I multiply by pi over 180, is equivalent to pi over 6. That's going to be important. I want to recognize that 30 degrees and pi over 6 represent the same angle. If you remember from the warm-up, the length of the shorter side is 1/2, and this is when we're dealing with a hypotenuse of 1. The length of the longer side is going to be the square root of 3 over 2. That means that if I'm looking for the ordered pair for that point right there, the x value is going to correspond to the length of this side. So the x value of this point is going to be the square root of 3 over 2, and the height is going to correspond to the y value. So let's go back to our unit circle. Let's plug that in. That means that my x value here is the square root of 3 over 2, and the y value is 1/2. Well, if I go directly across to my other degree measure or radian measure where I have the 6 in the denominator, notice that the distance from the x and the y-axis are the same. We're just in a different quadrant. So in this case, I'm still the same distance away on the x-axis, except now it's going in a negative direction. So the ordered pair here is going to be a negative square root of 3 over 2, and the y value is still positive. If I scoot down to below the axis, to the other pi over 6 angle, notice in quadrant 3, the x and the y coordinates are going to be negative. But the distance from the x and the y axes are the same as they were in the second quadrant. And then finally, if I go to my other pi over 6 angle, this is going to be a positive square root of 3 over 2 and a negative 1/2 in terms of my y value. Okay. Let's go and take a look at a 45-degree angle. We said if it's a 45-degree angle, then the length of this side is the square root of 2 over 2, and the length of this side is the square root of 2 over 2. Remember we said that 45 degrees is equivalent to pi over 4, because we're essentially cutting, if I think about, remember this is 1 pi, so if I'm cutting it by 45 degrees, that means I've cut it into quarters. So that's why it's pi over 4. And so that makes this ordered pair, the ordered pair associated with that point, the square root of 2 over 2 and the square root of 2 over 2. Notice that all of our denominators are 2's. So now I can go ahead and take that information and put it on my unit circle. So for pi over 4, I know I have the square root of 2 over 2 and the square root of 2 over 2. If I go to the pi over 4 point in the second quadrant, the distance from x and y are going to be the same, but I just have to pay attention to the direction. So in this quadrant, the x value is going to be negative, but the y value will be positive. In quadrant 3, they're both going to be negative. And in quadrant 4, x is going to be positive, oops, and y is going to be negative. And the last one, this corresponds to our 60-degree triangle. But remember, if I drop an altitude, that just makes, so that's 60, that makes the other angle 30 degrees. So it's just flipping around my 30-degree angle. So I'm going to be using the same numbers, the square root of 3 and 2 and 1/2, except they represent the opposite sides. So for a pi over 3 angle, it's going to be the other way. It'll be 1/2 because it's closer on the x-axis, or it's closer to the y-axis, I guess. And square root of 3 over 2 is going to be my y value. That should be a square root of 3, sorry. If I go into the second quadrant, now my x is going to be negative, but the y value is still positive. In the third quadrant, both are negative. In my fourth quadrant, the x is positive. It should not be a negative. And the y value is negative. Okay. So really, if you can simply remember what's going on in the first quadrant, and then just recognize the patterns that follow, it's really easy to reconstruct the unit circle. But you're probably wondering why on earth we're doing this. So let's go back to our trig functions. Let's see. Let's go back to our trig functions. So we're just going to talk about sine, cosine, and tangent. And you probably remember Sohcahtoa from your studies in geometry. So let's think about what Sohcahtoa means. If we have a right triangle, and let's say I call this angle theta. The side that is opposite theta we label as our opposite side. The side that is next to theta we call our adjacent side. And then of course we have our hypotenuse, which is the side that's opposite our right angle. And Sohcahtoa basically reminds us that if I want to take the sine of theta, the O and the H tell me it's just going to be the opposite side over the hypotenuse. The cosine, that's going to relate to the adjacent side over the hypotenuse. And the tangent is going to be the opposite side over the adjacent side. So now we're looking at our trig functions on the triangle and how they relate to an angle in a triangle. But I can also superimpose them back onto my unit circle and look at sine and cosine and tangent as they would apply on a circle. So take a look at the triangle that I drew here. It's essentially the same triangle I drew here. So notice that the y value corresponds to my opposite side, and the adjacent side corresponds to x. And my hypotenuse is just 1. So what I'm going to do is I'm going to take what I know about my unit circle and I'm going to relate my sine of theta to my unit circle. Well, like we said, the opposite side corresponds to y, and my hypotenuse is 1. So this reduces to y. So it turns out that the sine function is related to the y coordinate on my unit circle. Cosine is going to correspond to x over 1, which is just x. So cosine relates to x. The tangent is going to relate y to x. It's just going to be that fraction. So basically what we're saying is the point xy is equivalent to the ordered pair where we have the cosine of theta and the sine of theta. So what does that mean? It means if we use our unit circle, I can evaluate sine, cosine, and tangent without my calculator. Let's go back to my unit circle. I'm going to have to scroll up a little bit, so I might have to scroll back up and down. So for example, if I wanted to find the sine of, let's say, pi over 4. Remember, this is my angle. This is theta. So what I'm going to do is I'm going to look for pi over 4 on my unit circle. And remember that sine corresponds to the y-coordinate. So if I find pi over 4 on my unit circle, I'm going to look for my y-coordinate, which is the square root of 2 over 2. So I just evaluated the sine without a calculator. What if I wanted to find, say, the cosine of 240 degrees? Well, the 240 degrees gives me my angle. The cosine tells me I'm looking for the x value. So I'm going to find 240 degrees on my unit circle. And the x-coordinate of that point is -1/2. If I wanted to find the tangent, let's try doing the tangent of, let's do 3 pi over 2. Well, we know that tangent is opposite over adjacent, or simply my y value over my x value. So that's going to be -1 over 0. Well, try plugging that into your calculator. -1 divided by 0. Notice you get an error message. We cannot divide by 0. So the tangent is what we would say is undefined at 3 pi over 2. It's also going to be undefined at pi over 2. But suppose I wanted to find the tangent of pi. So I know I'm sort of running out of room. If I wanted to find the tangent of pi, I'm going to find pi on my unit circle, and I want to do the y value over the x value. Well, this time if I take 0 and divide by -1, I get 0. Oops, I did it wrong. 0 divided by -1. Sorry, I said it right, but I wrote it wrong. Because if I have nothing, if I split it up, it doesn't matter how many ways I split it up, nobody's getting anything. Everybody gets nothing. I could also do something like the tangent, or let's not do tangent, let's do the cosine of -30 degrees. So what is that negative telling me to do? Remember, the negative tells me the direction I need to go in. So I know that a +30 degrees is right here. So a -30 degrees is going to be the same distance, but I'm going to go in the opposite direction. So a -30 degrees is equivalent to a 330 degree angle. So I'm essentially trying to find the cosine of 330 degrees. And since I'm asking for the cosine, that means I'm looking for the x value, which is going to be the square root of 3 over 2. Suppose I wanted to find the tangent of, let's do -7 pi over 6. Okay, so let's think about what a +7 pi over 6 looks like. A +7 pi over 6 is going to take me all the way around the circle and then down one little piece. So if I'm going to go in the negative direction, I'm going to go the other way, halfway, and then one little piece. So a -7 pi over 6 is going to be equivalent to a 5 pi over 6. And since I'm looking for the tangent, that means I need to do my y value over my x value. And for 5 pi over 6, the y value is 1/2. And the x value is a negative square root of 3 over 2. Now, I understand that, I don't know that you guys have talked about compound fractions. That's what this is, when you divide a fraction by a fraction. But in elementary school, you did learn how to divide fractions. You just didn't make them look like this. When you did them in elementary school, it looked like this. 1/2 divided by negative square root of 3 over 2. And what you need to do when you're dividing fractions, if you remember, it's the same thing as multiplying by the reciprocal. And so when I multiply, I know these 2's are going to cancel, and that leaves me with a -1 over the square root of 3. And this is where it gets to be kind of a pain, because if you remember at the beginning of the lesson, I told you we can't leave our fractions with a radical in the denominator. So I'm going to need to multiply by the square root of 3 over the square root of 3, because that's just 1. But on the top, if I take -1 times the square root of 3, I get the negative square root of 3. And in the denominator, square root of 3 times the square root of 3 gives me the square root of 9. And that's going to reduce to 3. So that's what the tangent of -7 pi over 6 is going to look like. Okay, I know I've covered a lot. What I'd like you to do is press pause, and I'd like you to go ahead and evaluate those 4 functions. Okay, and if you've done it correctly, these are the correct answers. And that should be a negative square root of 2 over 2. So I hope this was helpful. If you have any questions, obviously you can come on in for Bulldog Block.